So just as a reminder, a vector is something that has magnitude and direction. So we're saying we're going 75 miles an hour in that direction. In 3 dimensions, we represent our vectors. So there's vector v. We use an ordered triple. So it's kind of like a point. So v1, v2, v3 with the angle brackets. And that's how we write a vector. We call this the component form of our vector. So this tells us the vector is so many units in the x direction, so many units in the y direction, and so many units in the z direction. And our x component is v1, our y component is v2, and our z component is v3. If we write v equals, we can also write it this way, v1 I hat plus v2 j hat plus v3. For our z component, we use k hat. And this is our standard unit vector notation. And our unit vectors, so I hat is a unit vector, means its magnitude is 1 in the x direction only, 1, 0, 0. J hat is a unit vector in the y direction, 0, 1, 0. And k hat is a unit vector only in the z direction, 0, 0, 1. You'll see that this first form, the component form, this is more, you'll see this more in math, and you'll see the second form more in science. But they mean the same thing. That whole mathematician, engineer, physicist thing. But we know which one is the best one. And then, oh, that reminds me. Now we can show this. Pretty nice. Yeah. It's funny on multiple levels. All right. All right. The zero vector. The zero vector is, we write 0 with an arrow over it, and that vector is the vector with zeros as our components. And the zero vector does not equal the number 0. Zero vector is a vector, zero number is a number. So they're not the same thing. All right, we good so far? Okay. Component form, if we have, a lot of times we'll be talking about when we're using vectors, we'll talk about vectors between points. And we did this before in 2 dimensions. If we want the vector between we'll say this point is, the coordinates are P1, P2, P3, and Q, Q1, Q2, Q3. So our vector goes from P to Q. To get the component form of this vector, do we remember what we did in 2 dimensions when we wanted a vector between 2 points? We had kind of a shorthand that we thought of. We do the way we thought of it was terminal. Someone said subtract minus initial. So the vector from P to Q would be in component form. Since going from P to Q, the terminal point is Q. Our x component would be Q1 minus P1. Our y component would be Q2 minus P2. And our z component would be Q3 minus P3. So we just do the terminal point minus the initial point and write that in our vector notation. That would be the vector from P to Q. Vectors are equal. Do we remember when vectors are equal? Or how we tell if vectors are equal? We have two vectors. We want to know if they're the same vector. Their components have to be the same. So we just compare the x component, the y component, the z component. They have to be the same for our vectors to be equal. We also work with the magnitude or the length. So if we have our vector v is in component form v1, v2, v3. The magnitude of v, or the length of v, we write double bars around it. And I learned it in older textbooks. They just use a single bar, so it looks like absolute value. It means the same thing if you're talking about a vector. That's the length. And we use basically the Pythagorean Theorem. v1 squared plus v2 squared plus v3 squared. That's the length or the magnitude of that vector. And if we drew our little vector, that's the hypotenuse of the little triangle there. It's basically the Pythagorean theorem. So all of these tell us the same thing, the magnitude or the length. Mm-hmm. Oh yes, that should be a plus. Thank you. And so do we remember now that we talked about the magnitude, we also found unit vectors. So we want the unit vector in the direction of v. You remember what we did to find that? Divided by the magnitude. V over the magnitude of v. So we just take our vector, divide it by the magnitude. That gives us a vector in the same direction, but its magnitude is 1, because we've divided out the magnitude from the vector. And all of this is the same as what we did when we talked about vectors in 2 dimensions. We just have this extra z part that we're going to use in 3 dimensions. Okay, we're good so far? All right. Addition and subtraction. Do you remember how to add? Do we remember how we added or subtracted vectors? So we have our 2 vectors in component form. How do we add them together? Add the components or subtract the components. That's all we have to do. Add or subtract. Add or subtract the components. So if we're adding 2 vectors together, we add the x components, add the y components, add the z components, and we get a new vector. If we're subtracting, subtract the x and y and the z, and we get a new vector. That's all we have to do. Scalar multiplication. Do you remember what we meant when we're talking about vectors when we say something is a scalar? What's a scalar? Just a real number. So we say scalar, so we know that's not a vector. So if we're doing, so let's say u equals the vector in component form, u1, u2, u3, and we want to multiply by a scalar, so ku. Do you remember what we do to multiply this vector by a scalar? Multiply each component. So we're just ku1, ku2, ku3. And what does multiplying by a scalar do to the magnitude? So say we multiply by 2. Doubles it. Multiply by 4, quadruples it. So that just multiplying by a scalar just makes our vector longer. Dot product. We learned one way to multiply vectors. What we're doing, where we're going with three-dimensional vectors is we're going to learn a different way to multiply vectors. That's what we'll talk about next time. It's called the cross product, and the cross product is something that you use as you move forward using vectors. So one way to multiply is the dot product. We're moving towards being able to do the cross product because that's something that you'll need to be able to do in future classes is find the cross product of vectors. Dot product. So if we have u in component form is our vector u1, u2, u3, and v is in component form our vector v1, v2, v3. We wrote u dot v for the dot product. You remember how we found the dot product? Multiply the components and add them together. u1, v1, so multiply the x components, plus u2, v2, multiply the y components, plus u3, v3. And we add all those together. So that was our dot product. One way to multiply vectors. We'll learn another way next time. Yes?
So in that, you're not finding a vector, you're just finding a number.
Right, and that's a good reminder. The dot product is a scalar. So the dot product gives us a scalar. Dot product you use a lot use extensively in physics when you're talking about vectors, when you're talking about motion. The dot product will give you the component of one vector in the direction of another vector, essentially. So it's an important thing that you use in science a lot. But another thing, what we used the dot product for was the angle between vectors. That was one way that we use a dot product. So when we're talking about the angle between vectors, our angle is between 0 and pi. So between 0 and 180 degrees. We said that the cosine of the angle between the vectors was the dot product divided by the product of the magnitudes. U dot v over the magnitude of u times the magnitude of v. That gave us the cosine of the angle between them. And this comes from the law of cosines. And if we multiply both sides by the product of the magnitudes here, we get another way of finding the dot product. We could say that u dot v is the magnitude of u times the magnitude of v times the cosine of the angle between them. This gives us another way to find the dot product. And with this way of finding the dot product, we don't have to know the component form. All we have to know is the magnitudes and the angle between them. So sometimes that can be useful. What does this tell us if u dot v equals 0? If the dot product is 0. So I get u dot v is 0. So I get cosine theta is 0. So what does that tell us about the angle? Theta is, what is it? Cosine of theta is 0. So theta is the y component is 1. But what angle? What angle are we talking about? 90 degrees. There we go. If u dot v is 0, theta equals 90 degrees. The angle between the two vectors is 90 degrees. We say the vectors are orthogonal. So if the dot product is 0, the angle between them is 90 degrees, we say they're orthogonal. And we're saying that the magnitude, neither of these is the 0 vector because we don't want to divide by 0 here. So the dot product lets us find the angle between vectors, and it also gives us a test to decide if the vectors are orthogonal. All right, are we good with our definition so far? All right, let's look at a couple of examples using these ideas, and then we'll talk about one other short topic, and then we'll be done with three-dimensional vectors. All right, so our example. We'll start easy. Thank you. We want the component form of the vector from 2, -4, 1 to the point 5, 7, 0. So what are we going to do here? Terminal minus initial. That's how we find our component form. Someone already started figuring it out for us. So we'll call it vector v equals. So what's our x component? 3, 5 minus 2. Y component? 7 minus -4, 11. And then -1. All right, now let's say, so we found our component form. Now let's find a unit vector. Let's find a unit vector in the same direction as the vector, as this vector, vector v. So we found the component form of this vector. Now we want to find a unit vector that points from 2, -4, 1 to 5, 7, 0. So what do we do to do that? Find the magnitude, divide by the magnitude. So our unit vector, u, is going to be v divided by the magnitude of v. So we need to find the magnitude of v and then divide by that. So the magnitude of v equals square root of 9 plus 121 plus 1. Just square each of these, put them in there. So what do we get? 131. So our unit vector, 1 over the square root of 131, and we don't have to rationalize that, times this vector. And that's all we have to do. That would be our unit vector in the direction of B. Yes?
Why is it 1 over 131?
Because we want to divide by the magnitude. So I'm dividing this by this. So I want to...
Where do you find more? Where do you get more?
So this, I could write this as, that's the same as writing, I'm dividing everything by 131, 3 over square root of 131, 11 over the square root of 131, negative 1 over the square root of 131. So I just divided this vector by 131. So I just factored out that 1 over 131 instead of doing it as division. So you could write it either way. Either way is fine. We're dividing everything by square root of 131. Yeah.
This is 1 because we are doing the unit vector. And the unit vector because it's 1, right?
I wrote it this way just because instead of writing v over the magnitude of v, this dividing by the magnitude of v is the same as multiplying by the reciprocal.
And what is the value of v?
What's that?
The value of v.
The magnitude?
The value.
Oh, this is our original vector. That's this vector. So we're taking that vector and we're dividing by its magnitude. So we divide each component by the magnitude. And instead of writing it this way, I can just factor out that 1 over square root of 131 and put it out front. The 1 over the square root of 131 is the same as dividing by the square root of 131. What if the problem asks us to find a vector with magnitude 5 in the direction of B? What would I do? Multiply this thing by 5. Multiply this by 5. So I could write it like this. Or I could write it like this. So that would be a vector magnitude 5 in the direction of that one. So that was another type of problem that we did with unit vectors. We found we can find a vector with any magnitude in the direction of this vector. All right, other questions there? Okay, let's find the dot product. So we have these two vectors, u equals, in component form, 262. And v is the vector in component form, negative 150. So we want u dot v. Dot product easy to find. So what are we going to do to find our dot product? Multiply component by component and add. So I get 2 times negative 1, so negative 2 plus 6 times 5, 30 plus 2 times 0, 0, 28. So the dot product is 28. All right, now let's apply this dot product to find the angle between two vectors. So this problem says find the angle between these two vectors. Before we do this, think about how difficult this would be if we didn't have this idea of the dot product. We have these two vectors in 3 dimensions, trying to find the angle between these two things with geometry or something. It would be kind of a challenging problem. Dot product makes it really easy. All right, so we know that the cosine of our angle is u dot v over the magnitude of u times the magnitude of v. So we have to calculate the dot product and we have to calculate our magnitudes. So u dot v, dot products are easy. U dot v is negative 2 minus 15 plus 0 equals negative 17. And the magnitude of u, magnitudes are pretty easy as well. Square root of, let's see, what do we get? 4 plus 9, square root of 13. The magnitude of v equals the square root of 1 plus 25 plus 1, so square root of 27. So theta equals the inverse cosine of negative 17 over square root of 13 times square root of 27. So before we even plug that into our calculator, let's think about this for a second. The cosine of our angle is negative. What does that tell us about our angle? Our angle is between 0 and pi, so between 0 and 180 degrees. And the cosine is negative, greater than 90 degrees. Our answer should be greater than 90 degrees, because on our unit circle, the x component is positive over here. We go up to 90 degrees, our x component is negative over here. So our angle should be greater than 90 degrees. So if we plug it into our calculator and the calculator tells us something not greater than 90 degrees, we've made a mistake. So when I plug this into my calculator, I get this is about 155.1 degrees. Bigger than 90 degrees. So that says at least we did something right here. So we can figure out things about the vectors just by the sign, S-I-G-N, sign of the dot product. It's positive, angle between them is less than 90 degrees. It's negative, it's greater than 90 degrees. If it's 0, it's at exactly 90 degrees. We get a lot of information from the dot product. All right, questions on those examples? All right, one last topic. You remember how to tell if vectors are parallel? There's a really easy way to tell if vectors are parallel. One is a scalar multiple of the other. So in symbols, that says U equals K times V. So if one's a scalar multiple of the other, we know they're parallel. It just means one's larger than the other, but they point in the same direction. So if your question says, are U, this vector 2, 6, 1, and V in component form is 1035, parallel. Yes, because Because what's our reason? 5u equals b. So b is 5 times as long as u. They're scalar multiples, so they're parallel. This reminds me. I argue with my wife sometimes about whether words. So could a vector be parallel to itself? Is a vector parallel to itself? Isn't it a scalar multiple of 1? So it'd be parallel to itself. So I argue with my wife whether or not words can rhyme with themselves. She says no. And I say, well, they have to. They sound exactly the same. My father-in-law, who's an English PhD in English literature or something, he says yes, words rhyme with themselves, but it's bad form to do so. My wife still doesn't believe that words rhyme with themselves. But vectors can be parallel to themselves by our definition. All right. Let's look at a little more challenging problem. Are the points P 1, 3, 4? Q is a point 3, 2, 7. And R 5, 1, 10. Collinear. Collinear means on the same line. Now, without vectors, figuring this out could be kind of hard. These points in 3 dimensions. Anybody have an idea of what we could do? Mm-hmm. So which vectors do we want to find out? So we want the component form of the vector from P to Q, and then we also want the component form of, we could do Q to R, but we want to make sure, I like to start at the same point. So from P to R. So if those lines are collinear, we should have something that looks like P, Q, R. So those are our points. So we should have something that looks like this. Here's my vector from P to Q, and here's my vector from P to R. One vector should be a little longer than the other, or some amount longer than the other. So basically, we're saying they're parallel. So we find the component form of PQ and the component form of PR and see if they're parallel. The PQ, finding the component form is easy. Terminal minus initial. So what would PQ be? 2, -1, 3. And PR, terminal minus initial again. 4, -2, 6. Are they scalar multiples of each other? What's our multiple? 2. PR equals 2PQ. They're parallel. So the lines are collinear, or the points are collinear. Nice, easy test using vectors. Otherwise, it would be pretty difficult in 3 dimensions. And equations of lines in 3 dimensions are quite a bit more complicated than equations of lines in planes. So you can't just find the it's harder to just find the equations and then compare them. All right, questions on that example? Another problem, sometimes I give this to my Calc 3 students, but we give them 3 points, the coordinates of 3 points, and we want to decide if the triangle is a right triangle, a scalene triangle. So we're finding all the angles in the triangle using vectors. Another interesting problem you can do with vectors, because you can find the angle between all 3 of the vectors and figure out all the angles in your triangle. It's another interesting. All right, last example. So we have the terminal point. Of vector v is the point, and I'm going to give us the component form of vector v. Vector v is the vector 1, 3, 5. So the terminal point is point Q, which has coordinates 2, 5, 8. Find the initial point. So what are we going to do? What are we going to do here? We have the component form of our vector, and we have the terminal point. How do we find the component form from our points on our vector? We could, well, I think you're thinking on the right track. What was our shorthand notation for finding component form if we had 2 points? Terminal minus initial, right? So let's call our terminal point P. And let's call that P1, P2, P3. So terminal minus initial, P1 minus 2 has to equal what? 1. Has to equal the x component. P2 minus 5 has to equal 3. And P3 minus 8 has to equal 5. So we're set here. P1 equals 3. P2 equals 8. And did I do that right? No, I did it backwards, didn't I? I did initial minus terminal. So I just need to turn these around. And this is our initial point, right? That's our initial point. So terminal minus initial, now we have it. 2 minus P1 equals 1, 5 minus P2 equals 3, and 8 minus P3 equals 5. All right, so P1 equals 1, P2 equals 2, and P3 equals 3. So P is the point 1, 2, 3. All right, questions there? Okay. All right, there we go.